Yesterday we started this lesson and we ended up with end behavior, right? So end behavior is a very important concept when you're trying to graph a polynomial of higher degree. Because once it's not a parabola, third power and higher, these graphs, they can have a lot going on. But if you can tell me what the endings are doing, then that's half the battle. The other half is the spaghetti in between the endings. So yesterday we got through end behavior. We talked about the end behavior dance, right? If the highest degree, the highest exponent is an even number, then your endings point the same direction. Positive people smile, negative people frown. So both arms up. This is even degree with a positive leading coefficient. Both arms down. Odd degree with a negative leading coefficient. Even degree. Crud. See, I swear, it's the caffeine. I swear it is. I don't know if the caffeine fries my brain or what. Let's try it one more time. Strike it. Strike it from the record. We'll try again. Okay. Even degree, positive leading coefficient, both arms up. Even degree, negative leading coefficient, both arms down. There we go. If you have an odd degree, the arms go different directions because don't I just look odd doing this, right? So one arm up, one arm down for an odd degree. If the leading coefficient is positive, then there is a positive average rate of change. So you can imagine if you could, quote unquote, connect the endings, you would have a straight line going up from left to right because there's a positive average rate of change. If the leading coefficient is negative and you could connect, quote unquote, the endings, then there would be a straight line with a negative slope because overall there's a negative average rate of change. Cool. So that is recap. Today, we're going to be talking about the zeros and the shape of the spaghetti. First things first, good old Algebra 2 question says, find the zeros of this polynomial. How would we do that? How would you do it, Kai? Well, if you plug in 0, that's going to give you the y-intercept. The zeros are the x-intercepts. So how would I, quote unquote, solve this equation?
Factor out an x.
Find what makes it equal 0, and what's the process? Factoring. We got to factor. So what we're doing is when you're finding the zeros, what you're doing is you're saying, okay, I need to know where my y values are 0. Because that means I'm on the x-axis. And factoring is the way to do it. McKinley said factor out an x. Yes, we are factoring, but she's noticed specifically that x is a GCF. At least I think it was McKinley. But we see that there is a GCF of x. So factor out that x, and it's going to leave you a quadratic on the inside. And that is factorable, yes, sir, because we are looking for two numbers that multiply to -6 that add to -1. That's pretty easy. -3, +2. Great. At this point, we would just find out what makes each of the three factors equal 0. We talked about it yesterday, but anytime there's an x outside of parentheses, its solution is always the same, regardless of what numbers sit in front of it. The solution for that x out there would be 0. Good. And then the other ones, you just tell me what makes the inside equal 0 by basically changing the symbol that you see in there. So I've got an x equals 0, I've got an x equals 3, and an x equals -2. Of course, those aren't in numeric order, but who cares? Well, that's easy. That's algebra 2. Factoring and setting the parts equal to 0. You could graph this if you wanted to, because you have knowledge of end behavior, and now you know where it crosses the x-axis. Sounds to me like you could graph it. You might not know what the y values are, but who cares? We don't really care. Y values are not that important. X values is where we're going to live. So in order to fully and deeply understand the spaghetti that is in between our endings, we have to talk about multiplicity of a 0. What does that mean? Well, sometimes answers repeat themselves. For example, I give you the quadratic. Y equals x squared, the parent quadratic. How many solutions does it have? Y equals x squared. no, meaning like where does it touch? How many times does that touch the x-axis? One time. Y equals x squared hits the x-axis one time at x equals 0. But technically, that quadratic does have two solutions. They just happen to be the same number. So we would say that the single answer of x equals 0 has a multiplicity of 2 because it was a repeated root. So sometimes when we factor, what we end up with is a set of parentheses that has an exponent on it. What that means is that answer has a repeated answer. It could be repeated 2 times, 3 times, 4 times, whatever. The exponent on the set of parentheses is the multiplicity of that root. So if we have an exponent m, then we could say like m is 2 or m is 3. Then we could say that c is a 0 with multiplicity 2 or a 0 of multiplicity 3. It says that m has to be greater than or equal to 2. That's because if a set of parentheses does not have an exponent, that exponent is automatically a 1. Does that make sense? Anything that doesn't have an exponent, we could say, well, technically it has an exponent of 1. So you would say you wouldn't say it's a single multiplicity. It doesn't make any sense. But you could tell me, oh yeah, that root or that solution has a multiplicity of 1, and I would understand that you meant it had an exponent of 1. Okay? It wasn't repeated, but we know it had a 1. So what matters is whether or not that exponent is even or odd. That's what matters. Is the exponent even or odd? Not the solution. Nobody cares if the solution is even or odd. It's the exponent. When the exponent of a root, meaning a set of those parentheses, when the exponent is even, then what we say is the graph bounces off of the x-axis at that point, which is what you're seeing happen right here. See, it touched the x-axis, but it bounced off of it. It did not cross through it. If a root, a set of parentheses, a solution, has an odd multiplicity, meaning the exponent is odd, then the graph will cross through the x-axis at that solution. So you're seeing that happen here, and you're seeing it happen here, passes right through. So maybe you have noticed that the odd multiplicities have more than one shape. You have one that crosses right through it like a straight line almost, and one that crosses through it and kind of looks like a cubic, right? You guys see that? Well, guess what? That shape is telling you what the multiplicity of that root was. It's telling you more than the fact that it's odd. You see how this one right here is shaped like a cubic? Yeah, what it's telling you is that the exponent on those parentheses was probably a 3. It could have been a 5 or a 7 or a 9 because any odd exponent that's bigger than 1 is shaped, quote unquote, like a cubic. But you just assume that it's a cubic. So this looks like x plus 2 to the third. Now, where my graph is going through the origin, you see how its general shape right around the origin looks like a straight line? Well, straight lines are linear. Their exponent is 1. So what that would tell me is that right here, whoop, it looks like I just have an x to the first. Now the even multiplicities, when they bounce off the x-axis, they always look the same. They bounce. It could be any even power. But you remember yesterday when I was talking about the quartics? And I said the 4th power is parabolic, 6th power is parabolic, 8th power is parabolic. The only difference is that the parabola kind of flattens out at the bottom. Remember I told you that? That one's not very, quote unquote, flat at its bump. I don't want to say it's vertex because it's not a vertex. But you see how it's kind of shaped like a parabola? That's how we know that it's probably an x squared right here of some sort. So this looks like x minus 1 squared to me. Yes?
So if it says x plus 2 to the third, why is that negative?
Well, because it's called a 0 because what makes the inside equal 0? -2, yeah. So because it's just like when you factor, we always want to switch the signs. And it's the same thing that happened over there with the x is hitting the x-axis at 1 without crossing through it. That root, the set of parentheses, says x minus 1. So if I wanted to write the equation of this graph or write an equation of this graph, I could. Yes, ma'am. Well, don't think so much about the quadratic, but if you were trying to, I think what you're getting at is the fact that both endings point down. Both endings point down. So what does that tell you about the polynomial? It's even power, and it's got a negative leading coefficient. That's what it tells you. So both endings pointing down tells you that the exponent is even, but you know that the leading number had to have been negative. So I could have written this as f of x equals negative. Now I don't care, honestly, what the y values are. Pretend you can't see them. They're unimportant. All that matters is x. If you were to graph the equation I just wrote, it would look somewhat like the one that is on there. Now, to be honest, its bump at the local maximum would probably go a lot higher than what you see in that picture. And the bump at its local minimum between 0 and 1 would probably go lower, but who cares? We don't care about y values. What we're going to say is this graph behaves like the fuchsia f of x that I just wrote. And if you have any questions about how I wrote that equation, please say something, talk to me, let me help you. Maybe you're looking at that and you're going, how would I know that that's an even power? You know what I mean? I mean, how would you have graphed that? You know, you need to know the end behavior. How would you have known? Well, watch this. On this, after my negative sign, on this x, what is its exponent? 1. Well, just add the exponents. 1 plus 3 plus 2? 6. That tells you it has an even degree, which means the endings point the same direction. And then the negative sign on the front tells you, oh, they must both point down.
Does that mean it's an even function?
It does not mean it's an even function. When you say something is an even function, you're implying that it has even symmetry, which means it's symmetric over the y-axis. So we have to say it's an even degree polynomial. We don't want to say it's an even function. I know that's wonky, but we have to be very careful about those words. Is it possible for an even degree polynomial to be an even function? Sure it is, but it's not a guarantee. There was a question on my Zoom.
Yeah. How can you tell if m is a repeated 0? I mean, I don't quite understand. Just because it's greater than the m is greater than 2, like if it was a 4,
So just by
that means
looking,
it's a repeated
just by
0?
looking at the picture, you mean? How can you tell if it's repeated or not?
I mean by looking at the equation.
Well, if you're looking at the equation, you just look to see if the set of parentheses has an exponent. If it does, so McKinley, I have written here x to the first and then x plus 2 to the third, x minus 1 squared. You know that x plus 2 to the third means I could have written x plus 2 3 different times, right?
Yes.
That means it would have been repeated 3 times. And that x minus 1 squared could have been written as x minus 1 times x minus 1, which means it was repeated twice. So if the set of parentheses has an exponent on it, then it has a multiplicity bigger than 1. So if you have an odd exponent on the answer, then your graph is going to cross right through the x-axis there. And it can either look like a cubic or it can look like a straight line, just depending on that odd exponent. If the odd exponent is a 1, it goes right through it like a straight line. If the odd exponent is 3, 5, 7, yada, 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 it gets an inflection point at that 0. Looks like a cubic. Now, if a set of parentheses has an even exponent, well, then it looks like a parabola at that point. It bounces off the x-axis without going right through it. Cool? Any more questions? He's good. No? All right. So let's sketch this graph. It says state the degree and then list the zeros. Let's start there. We'll state the degree and we'll list the zeros. What is the degree of this polynomial? 5, because you have to add the exponents of 3 and 2. Remember, I could have written this out like this, and don't write this, I'm going to erase it. But I could have written it like this. And if you foiled this whole long mess out, you would have x to the first, second, third, fourth, fifth at the very front. You'd have an x to the fifth at the front. Let's see. Let's get fancy on them. Nope. Try again. There we go. Gone. Okay. So our degree is 5. Time to list our zeros. Zeros are places where a graph crosses the x-axis. At x equals, where's the first time we cross the x-axis? -2. And the other time we cross the x-axis, x equals +1. There's our 2 zeros, and I left space in between them for a reason. It says to state the multiplicity of each zero, and then say whether or not it crosses the x-axis or bounces, basically. So let's see. At x equals -2, I'm referencing this set of parentheses. It has an odd multiplicity. So what does that tell me? Does it bounce off the x-axis or go through the x-axis? It goes through. So it goes through at x equals -2. And more specifically, because it's a power 3, it will look like a cubic there. No, it looks like a cubic because technically the polynomial is the 5th degree polynomial is not a cubic. It's going to have wiggles in it. It's going to have wiggles. And at x equals 1, we're referencing, we do use a different color. Let's use purple. Referencing this set of parentheses. Its exponent is 2, so do I go through the x-axis or bounce off the x-axis? We bounce. Which means it's going to look like a parabola of some sort. I don't know if it's up or down. I'm just drawing what our general shapes are going to look like. Now we get to sketch this graph. Remember, nobody cares what the y values are. Unimportant. You don't care. The only x values that matter to me are -2 and +1. Doing my best to get picture drawn to scale, for the x's at least. All right, now I'd like to draw this graph, but I have a problem. I don't know what the endings look like. That's right, we learned that yesterday. Well, we just said it's a 5th degree polynomial, so what does it tell you about the endings? Kai did the arms, but yeah, 1 up, 1 down. 1 up, 1 down. Guy with the broken collarbone says, I wish I could do that. That's funny. 1 up, 1 down, okay? Now the question is, the leading coefficient, would it be positive or negative? If you were to have foiled the whole thing out, do you remember what I said would be at the front?
Positive.
X to the 5th, which would have been positive. So I'm just going to write that, positive leading, because that tells us what our endings look like. We know we have an odd degree polynomial. Catch up with me, panel. What is going on right now? There we go. Positive leading with an odd degree. That means our endings go left, down, right, up. Yes, question. Positive leading coefficient, because if you were to FOIL out all 5 sets of parentheses, no, you don't have to, but you see it, because this one would have had an x to the 3rd, and this one would have had an x squared, and eventually you would have had to have multiplied those, and you would have gotten an x to the 5th. But the number in front of it is +1. Yeah? Well, I mean, what, x plus 1 squared? That gives you x squared plus 2x plus 1. If you multiply by another x plus 1, now the front is x to the third, but it hasn't changed sign, has it? So the front things will tell you if you're going to be dealing with a positive or negative. This one's positive, so we know left up, right down. So what you do is you come over to your sketch and you draw left up, left down, right up. I think I said the wrong thing a minute ago. Like that. And now your multiplicities, they fill in the spaghetti. At -2, I know I'm going to go through the x-axis, but I'm going to go through it like a cubic, which means I have an inflection point there. And I know that the graph is going to have to come back down eventually and hit x equals 1, right? I mean, we see that it's a 0, so I know my graph has to hit x equals 1 again. And we know because of the multiplicity that I bounce off x equals 1. So it looks like this. There. Where exactly is that local maximum on the x-axis? You don't know, and you don't care right now. That's calculus. We'll do it at the end of the year. How high up does it go? You don't know, and you don't care. That's the answer, okay? As long as you can give me the general shape, you're in good shape.
We have one of these on the test?
Yeah, there's these on the test. So do I have any questions for this one before we move on to our last example?
We've got
2 more examples? Okay, no worries. No questions? All right. Holy crap, look at that guy. It says find a possible equation.
Why?
Notice there are no y values. You see that? That's because who cares? They're not important. Nobody cares. We're looking for a possible equation. What you're going to do is you're going to first find your zeros. Let's mark those bad boys. I've got a 0 here, and I've got a 0 here, and stupid box got in my way. There we go. This thing has 4 zeros. That tells me that it is at least a 4th degree polynomial. At least.
Probably more.
It's probably more. Actually, it's guaranteed to be more. Why can't it? What's that?
it can't be a fourth because it's
There we go. So it can't be a 4th degree polynomial because its endings point 2 different directions. So we know it must be more than 4. Well, why don't we talk about multiplicities? Let's see what's happening right here. At this number, my graph is shaped like a cubic. So more than likely, right there, the exponent on that root would have been a 3. Well, that's a terrible 3. What would go inside those parentheses, though? X plus 4. Yeah, that's what would make a 0 at -4. X plus 4. Oh, you mean for the end behavior? We'll get there. But yes, but we'll get there. So what you were trying to do is you were trying to make the polynomial have its negative symbol from the inside of the parentheses. Not necessary. You either when we're finished putting our parentheses together, we will put that plus or minus sign in the front. That's just where it would be. Now we have right here my graph bouncing off the x-axis. More than likely, that would mean the exponent on that root is a 2. Could it be a 4? It could be, but it's probably a 2. Oh, it's crossing through the origin. So what would that root be? Yeah, it's just x. And we know it's a square because it looks like a parabola there. Right here, at +2, I'm going right through the x-axis. But I'm going through it pretty straight, right? So the exponent on that root would probably be 1, linear, because it looks like a straight line. It's going through at +2, so inside these parentheses should be what should be in them? X minus 2. And lastly, right here, this set of parentheses, I'm going to make those parentheses just a little bit bigger so I can write larger. It's, sliding right through again and looks pretty straight to me, so its exponent would be more than likely a 1, actually extremely likely a 1. And what would it say to give me x equals positive 4 as a solution? X minus 4. Awesome. Let's put the polynomial together. We're not finished yet, but let's get it started. And order does not matter when you're multiplying, but usually x's that don't have parentheses sit in the front. So x squared, and then from there I'm just going to list them from left to right. X plus 4 to the third times x minus 2 times x minus 4. There. That is a 1, 2, 3, 4, 5, 6, 7 degree polynomial. All I did was add up the exponents on the roots, because the two sets of parentheses that don't have an exponent written are power 1. So I just added 1, 1, 3, and 2, so that gave me a 7th degree polynomial. All right, it's odd. It's an odd degree polynomial. We see one end is up, one end is down. However, if you were to connect those endings over time, there is a negative average rate of change. So the front number, the leading coefficient, positive or negative? Negative. There you go. Finished. That is good enough. You don't need to know if there's a vertical stretch or shrink. It's unimportant because there's no y values. And I'll be waiting for you to hit me with questions, comments, and concerns. Yeah, you could just look at it. That's the power of end behavior. Yeah, you could just look at it. Now, is there probably a number out there with a negative sign? Yeah, but since we have no y values, we don't care. Cool? And if you were to try to graph this thing that we just wrote on Desmos, those bumps, especially that maximum, skyrockets. Holy cow, is that a big number? I had to use a ridiculous vertical shrink to make this even fit on an image that went from x equals -5 to +5. But you don't need to know that. But it was like, it's something like 0.0001 or something like that. I mean, it's just stupid small. It's a ridiculous vertical shrink to make this fit. But it's fun, isn't it? Look at that graph. Wow. It's just fun. Look at wiggles. Skitties. All right, moving on. Designing a box. Huh? Got a question for me?
Like a snake. A little snake.
Yeah, a little bit of a snake. A company has contracted, well, I think it's supposed to say was. Okay, that's definitely a typo. A company was contracted to make boxes with a volume of 484 cubic inches. Boxes. Oh, let me do boxes. Let me draw me a box. I can do this. I can do, oh, you know, boxes are usually brown. Boxes are usually brown, so let's go ahead and do that. Well, we have a box, and it says squares are to be cut from the corners of a rectangle piece of cardboard, and then the flaps are folded up. So what we have here is a rectangle, picture not on scale. I cheated. I used a tool, and we are going to slice some squares out of the corners. We did it this year. Yeah. And you did it in Algebra 2, maybe. I'm not sure. So there we go. Let's see. It says squares will be cut from the corners of a, 20 by 25. So originally this thing was 20 by 25. That's what we had originally. Flaps are folded up. They make this box. It says, what size square should be cut from the cardboard? Well, what we know here is that our volume equals 484. How is volume of a box found? Length times width times height. Yeah, okay. So volume is length, width, height. Great. I don't know how big these squares are that I'm cutting out, right? So I'm going to call them x's. It's a lot of x's. But when you fold this box up, you're folding the flaps. And when you fold the flaps, this side touches that side. And they become one side, which would be that side. They would be that side. They'd be the height. What we need to do is figure out an expression for the length and the width. If the original, let's say width, okay, was 20, and I chopped 2 boxes off of it, 2 squares, what is its length now? 20 minus 2x. So this distance from here to here is 20 minus 2x. Let's see if I can write that sideways. 20 minus 2x. Ha, like a boss. That is here, 20 minus 2x. And what I need now is an expression for this length. If it was originally 25 and I carved those 2 squares out, what do I got? 25 minus 2x. Awesome. 25 minus 2x. We'll say that is there. Cool. All right. Volume. I have a number for that. It's 484. Length, width, height. I have expressions for those. X times 20 minus 2x times 25 minus 2x equals 484. Okay. How should we solve something like this?
Multiply it out.
Multiply it out. Yeah, you could. Those could be really big numbers, though, don't you think?
Will live.
What am I getting at, guys?
Just solve.
Bless you.
Solve for the insides.
Yeah, we're solving for x. Yeah, we're solving for x. Okay, how about this? Let's we've done a question like this before already. You know there's restrictions on my x's, correct? What's the smallest number x is allowed to approach?
0.
It's allowed to approach 0, but it cannot equal 0. But I need to know what its biggest number that it can approach is. What's the biggest number x could approach?
484.
Oh, no, that's the volume. The volume's 484.
20 minus 2x.
It can 20 minus 2x is the smaller side, so what's the biggest number x could approach?
12.5.
10. If x is 10 or more, well, x equals 10 tells you that this side has a length of 0, impossible. And if x is anything bigger than 10, this side has a negative length, impossible. So our answer must lie somewhere between 0 and 10. Guess how we're going to solve it? Technology, that's right. We're not doing this by hand. You kidding me? What's wrong with you people? No, we're using technology. So when you're doing questions like this at home, you're using Dr. TI or Dr. Desmos to solve for x. I'm going to use the graphing calculator so I can teach you how to do it. Just waiting on my graphing calculator program to start. There we go. Bloop. There we are. Okie dokie smoky. Y equals. I'm going to go ahead and clear that because that's from a different class. And I'm just going to put our polynomial in there that we found. We had an x, and then in our set of parentheses, we had a 20 minus 2x. And then in another set of parentheses, we had a 25 minus 2x. Now we're trying to figure out where it equals 484, right? Okay. We want to know where that polynomial hits the y value 484. Just giving some time for you guys to get it typed, those of you that are trying to. You don't have to, but you know.
So can you not just put this into the calculator as x 20 minus 2x plus, and then 25 minus 2x equals 44? Shouldn't this calculator solve it for you?
So our graphing calculators, the 84, does not have a computer algebra system on it, so it cannot do solving for us. The TI Inspire can, and the TI 89s can, and better than the 89s, but the 84 is the last line before the calculator can actually do the solving for us. But what we can ask the calculator to do is graph these two things. We can ask it where they intersect. Now I'm going to go ahead and hit my window. I'm just going to go ahead and hit window because here's the thing. We know that the x's are going to land between 0 and 10. We already know that. So we might as well just restrict our x values from 0 to 10 right now. X scale can go by ones for all we care. That's fine. Now our volume. All right, let's check this out. The minimum volume that makes sense is 0, right? The volume that we're trying to target is pretty close to 500, right? Now, because I'm crazy, I like my answers to questions to land somewhere in the middle of the screen. So since I'm targeting a y value of around 500, I'm going to make my y max 1000. This means my horizontal line at y equals 484 will be pretty close to the middle of the screen. I just like that. And I'm going to have my y scales go by hundreds. That way there's 10 tick marks there as well. And we go graph. Whoa, wait a minute. How many answers are there?
Mine has a second black line. Is that supposed to be there?
No,
What do I do?
that's your x-axis.
No, my x-axis is at the bottom. There's another black line above the x-axis, but below the red one, and I don't know what to do about it.
Go to y equals. It means that you have a line. Go to y equals. Let me see it.
But I don't.
Let me see it.
I just have these two.
I don't know. I don't know. I'd have to have the calculator in my hands to figure that one out. Anyway, look, we have two answers. Isn't that cool? Two different sizes of x that can be cut out. So we have to find them both. Second, trace, intersection, intersect, 5. So it says, hey, is this one of the curves you're looking at? And you go, yes, with the enter key. It says, is this the other one? And you go, yes, with the enter key. And it says, hey, take a guess. So you're just going to scroll on over to one of the two answers. It doesn't matter. And I'm pretty close right there. Gave me 1.22 as one of my answers. Neat. Do it again to get the other answer. Second, trace, 5 is intersect. And I go, yes, that's the first curve, and yes, that's the second curve, so it's nice when it's in color because you know exactly what it's talking about. It says, take a guess. And you go, all right, I'm gonna go way over here to this guess. So the first answer was 1.22. This answer is 6.87-ish. And there you go. Now you know. So we actually have two different possibilities here. Just means that we could either have a tall box or a squat box, whatever. But we found that x equals 1.22 or x could equal, was it 6.87? Woohoo! There you go. And that is the end of lesson 2.3.